So here we have the chromatograms shown in the plugin software, the simdist DHA plugin software, Eclipse, hydroporter tool. On the top chart, we can see the black line is the chromatogram from the crude oil itself, which will be blank subtracted. And below that, in a sort of pinky color, is our alkane calibration mix. It's going to map across the software. So the software will handle all this for us. And what it will do is it will create the simdist curve. As we've seen, this is the blue line in the bottom. And actually the black line, you can see we've dropped the baseline a lot in the bottom because that's the correct way. We've taken away the carbon disulfide on the bottom plot itself. But for the software itself, it's because it's been pre-calibrated with the pink alkane mixture, it's got the retention times of the alkanes up to C100. It can automatically process the sample and slice it for us and build the boiling point all the way up to, you see here, 730 degrees Celsius. So this is the simdist, the blue line is the simdist plot without any DHA analysis added. This is the analysis straight away from the simdist software plugin. Now, the issue we're going to have with this analysis, especially at the really lower boiling point ranges, is the influence of the carbon disulfide, because it obscures the bottom elution of the really light material in the crude oil sample. There is some quenching factors in the software, but what would be better is for us to run a DHA analysis and add to the very bottom of this curve, which is quite an important area. It's where the naphthas are, so it's really important for us to get this information. It makes it much more accurate when we combine it, as we'll see. So when we take this this is for our first sample from the simdist application, and then what we can do is if we run our DHA analysis, we get a lot more accuration where the blue line is the start of the distillation. And you can see it's a very steep curve at the start. So being a steep curve is that we would want to make it more accurate because when we move up the curve, we're moving up boiling point, and it will will improve the accuracy of the recovery, the yields, the information that we have at the bottom range. Because when we get into the simdist curve, it's much more gentle, it's much more straighter. Whereas in contrast, the curve for the DHA analysis, where even for the simdist down at the bottom range, is very steep and very quick. So by running the DHA analysis, we get a much more complete and accurate boiling point distribution. So moving on to the DHA analysis, we're going to run the samples under the astm method D7900. So again, we're going to run a calibration mixture, only this time from pentane up to C9, nonene, for the straight chain alkanes. And what this time, we're not going to calibrate against boiling point. We will use boiling points in the calculations. It will use that, yes. But first, we're interested in really calibrating it against the COVAX index, because inside the software, there's a big database, and it has a large number of organics, hydrocarbons listed with their COVAX index that we will be able to reach into and find out what compound was eluted at that retention time. So we'll run two samples this time, a calibration mixture and a crude oil sample itself this time. But instead of adding carbon disulfide, we're going to add a little amount of an internal standard to be able to do the merge of the DHA analysis. We're going to merge these results with the simdist results. So there's our calibration mixture from pentane, hexane, heptane, octane up to nonene. Now, by definition, pentane C5, COVAX index 500, hexane C6, 600, C7, 700, 8, 800, 9. So they, by definition, that's how they are set out for a COVATS in the database. And what we'll do is that when the unknown, or from our DHA analysis, we'll be able to find the retention time, and then from retention time we'll look up the database, and we will be able to infer what that compound is likely to be. The software uses more than just the retention time. It'll use a little bit of information that you do in what's called presets. You can tell if it's more a reformate, or what sort of history the sample is, and that will guide the database in a certain way when it looks up the COVATS database, and it will then label the peak for us. So that's the calibration mixture. So that will calibrate the COVATS for us. And then we can run, when we're only going to run the front end of the crude oil, we're not going to run the whole crude oil sample, just the front end. You can see we've added 1 hexene as the internal standard. So that there you can see the front end of the crude oil sample. The hardware we're going to use for that for the analysis of the front end as follows. So we've fitted a splitless injector. So unlike the simdist, which uses a codon column, we're going to be using the splitless injector this time. Again, detector wise, we're using an FID, but we're going to use a backflush. So we've got 2 columns, a pre-column followed by the main analytical column, and in between we're going to have a additional carrier gas source on a pressure regulator, an electronic pressure regulator, that will allow us to backflush the pre-column, because we're only interested in the up to C9 on the crude oil sample, because we've already got the information from C9 upwards from the simdist column. For the distribution, it is the very volatile material that we want to get information from the DHA analysis. So again, this can be fitted into a 436 GC if you want something nice and compact and you want high throughput. You can easily fit it in a 436, but we can also fit it into a 456 GC if you wanted to run other DHA analysis as well. So you can see that there's a 436 GC with the capillary column fitted into the oven space, which is just a normal air-cooled fan oven that we have, and it's also fitted with an auto sampler on the top for automated injection. So the columns we're going to use, the pre-column is quite a long column. It's 20 meters, it's 0.25 millimeters internal diameter with a 0.25 millimeter micron film thickness. And then for the main analytical column, we have fitted a very long 100 meter DHA 0.25 ID internal diameter with a thicker film, a 0.5 micron film thickness. So that's the setup. We're going to inject onto a splitless injector. We can use helium carrier gas. We've got our pre-column, which we're going to backflush all the heavier material off, because we're going to only put the light materials up to C9 onto the main analytical column. And then we've got a backflush in play so that we can backflush the heavier material back out the splitless injector. So here's the injector itself. This is our standard splitless injector. Well, very much like the cold and column injector, it has a very short nozzle that protrudes into the oven, low dead spots, cold spots into the oven. Now, unlike the cold and column, it's not a programmable heater that's attached to its isothermal. It's quite a large liner volume that's inside this injector, sort of approaches 1 mil maximum is the volume inside. So it's a large volume liner inside, allowing very capable splitless. What's quite unique about it is it has a split vent line at the top of the injector and also one at the bottom. So that makes the solvent tail for the split and splitless injections very sharp, well defined. So let's look at the parameters that were used for this analysis. So here we have screen grabs from the Compass CDS software that was controlling the GC. So on this one, we're heating up the splitless to 275 degrees Celsius. It's held there for the duration. Splitless does not have a programmable heater on it. It's an isothermal injector. It does have a split, so unlike the cold-on column, which there was no split involved, it doesn't have a split line, we're actually going to split this. So in this example, we've employed a 1:100 split ratio. And then for the helium carrier gas that's being used as a carrier gas, we're going to pressure program the carrier gas. And that will allow us to backflush the instrument itself. So initially, we have the pressure on the head of the column or the injector, the inlet, at 53 psi, and it's held there for 45 minutes. And then after 45 minutes, we're going to drop the pressure down to 23 psi, and that will allow us then to backflush the pre-column. So it'll backflush the pre-column out the split line at the split vent after 45 minutes, because we're not interested in the heavy materials, we are only interested in the light materials. As we say, we've already got the information of the heavier materials from the simdist method. What we want to do is complement. We want really more information, more accuracy at the front end. So we're only doing DHA on the front end of the light materials. So we have incorporated a backflush. This avoids luting all the heavy tarry residues onto the analytical column, which is not required. So here we have in the middle, between the pre-column and analytical column, we have this EFC 24 pressure regulator. It's an electronic pressure regulator, and it's got a set point, a static set point of 45 psi. So what we've done is we reduced the pressure on the injector down to backflush the pre-column. So the column oven program is set out here. You can see the screen grab here from the software, from the Compass software. So we're starting at just above ambient at 35 degrees Celsius, and we're holding that for half an hour, 30 minutes. So quite a long hold, so that you get full resolution. And then we're going to ramp it quite slowly, quite gently at 2 degrees Celsius per minute, up to 115 degrees Celsius. And then when it gets to 115 degrees Celsius, we're going to ramp at 10 degrees per minute up to 200 and hold it. So it's quite a long, it's 83.5 minutes long analysis. It's all automated. So there we come to the FID. So it's the identical picture. The difference is we've got no special fittings, no special ferrules, no additional insulation. So it's the same FID, but we've not enhanced it to take the temperature. Its maximum temperature is 400 degrees Celsius. So we're using FID detectors. And again, you can see actually we only really require it to be at 300 degrees Celsius for this analysis. We have increased the data rate up to 20 hertz. Again, we're using a makeup gas. Nitrogen is our favorite. You can use helium. We've turned it up because we're using a lot lower flow, so it's now at 28 mils a minute. But standard, we've got the hydrogen at the same 30 mils a minute and air at 300 mils a minute, as we normally would do. And just like the simdist GC, we can have got a choice of the same choice of auto samplers that can be used. I'll just skip over that. We've talked about that earlier. So I've two GCs because we've got a simdist analysis that goes up to over 400 degrees Celsius. It's too hot for the DHA columns. It will degrade them. It will. It's not really good for the film thickness. It'll just degrade too quickly and we'll lose performance. So it's not. We can't really put the DHA columns inside with the simdist GC. We're going to have to use two GCs for this analysis, but we can use one PC to control the two GCs. So we can use one software package with the two GCs. In this arrangement, we've got a standalone PC here, easily controlling the two GCs, and the data and the reporting will all be done by the plugin itself. So it's quite good actually to really have them attached to the one PC for the data analysis. So here's a screenshot showing the sample setup. Compass itself is used to control our GCs. It's used for the GC control, the data acquisition. It will collect and record the chromatograms, and it's very, very small on the screen, but right at the end is our plugin that we'll be using. It's the one last icon on the second row is the Petri Reporter plugin. So we will export, or we'll call in the plugin to process the data. The plugin has the database, it has all the information. It will take the chromatogram and it will do the post-processing for us. But the starting of your sequences, your acquiring of data, the control of the GC will all be done with Compass. As you can see here, I've got a sequence ready to go for the simdist GC and another sequence ready to go below it for the DHA analysis. It's the simdist sequence that's shown here on the right hand side. It has it's got a sequence of 5 samples to run. I can put the run information which will be carried through to the simdist application. So they're going to run for 40 minutes. I'll tell which file it needs to inject for the autosampler. I'm only going to inject about 0.2 of a microliter. That's more than enough sample for the analysis. And then to coordinate, to link to the simdist software to make it more automated, I can call in variables called preset names. I can add sol being solvent, calibration, a response standard, the sample itself, and at the end I've actually rerun the blank just to see what the blank is like. So there's a normal sequence for the setup of that will allow us to set up and calibrate the simdist software, the plugin, and run our crude oil samples. So once I've run the sample through Compass, the plugin will come into play, and using the algorithms that are built in behind the Eclipse Petri reporting tool and the databases behind it, it will be able to report our samples. Both, it will be able to do a simdist report from the simdist sample. It can wait, and we can do a DHA analysis. And then what we can do is with the DHA, we can merge the two reports together and get a single combined crude oil distillation, including this from the DHA. It's all handled by the Eclipse software, the plugin itself. Behind it, it's got a Microsoft SQL server, a database behind it that will hold in the retention times, the Kovacs indices, the properties of all the hydrocarbons that will allow it to automate the reporting. So you can see here on the main screen, a screen grab from the Eclipse Petri reporting tool. You have an analysis here on the left-hand side. We have a chromatogram in the middle. This is for the FID response standard and the validation sample. And in pink, we have overlaid the alkane retention time versus boiling point calibration chromatogram samples. You can see here, and on the right hand side, we can see the presets and of the sample itself. So that is a screen grab of the Eclipse software itself. Behind it, as I said, there's databases that allows the software to run its algorithms, to do the reporting. Here we've got the DHA component editor, so you can actually fine-tune the database as well. You've got full access to it, and you can see here it's got all the hydrocarbons. We're looking at the C8 hydrocarbons here. There's dimethylhexane. I can see here isoparaffin. So it can do piona analysis. It's got them listed into their groups, whether it's a paraffin, an aromatic, cycloparaffin, and alongside here it's got its index, its COVAX index, so that it will already be able to automate calculating the COVAX index for the unknown peak and then comparing it with the database to label the peak. We can also gear the algorithm for whether it wants to look biased towards more alkanes. So there are some other presets we can add to the search tools when it's looking up the database. And inside the database, you can see it has the boiling point, also has specific gravities, a lot more information inside the database itself. So that allows it, the software will then work together, and it will then produce our combined simdist report, as we can see here. Yes, we can plot chromatograms. We can plot the DHA curve. You can see in blue here on the left-hand side, we've got the simdist plotted from the DHA analysis, adding to the main simdist curve, the black line from the simdist analysis itself. And the chromatogram itself is from the simdist plot. We can, the software itself will create a distribution report for you, a table. It can also do a table of the cut points for you, and it has other reporting options as well inside it. So that really completes. I'm now sort of come to the end. I'm using up my time now. I see we've got about 5 minutes left. So the hardware of our gas chromatograms, fitting with the right columns, that we can do a combined simulated distillation to D7169, and also taken with the detailed hydrocarbon analysis, the 79, and with some sophisticated software, we can create PDF reports. We can also export to Excel. This is also really set out now in our application note. So there's an application note 88, which is available on the web page. It all sets out what I've just been talking about earlier in this webinar in more detail. If you need to contact us, you can use our website at scioninstruments.com. So I hope you've enjoyed this hour looking at the boiling point distribution of crude oils. It's giving you a little bit of information between the hardware and the software that we can use gas chromatography to help with the assay of crude oils. So thank you very much. If you've got any more questions, put them in the chat and we'll try and answer them. And I hope you have enjoyed this webinar, and thank you for listening.